Here we are. Chapter 2, Exercise 38. Prove that for all sets the following are valid. A is a subset of C and B is a subset of C if and only if A union B is a subset of C, and B, C is a subset of A and C is a subset of B if and only if C is a subset of A intersect B. Finally, we are at the very last exercise of Chapter 2. I am so excited. I can't wait to be done with this one. So, let's get this finished. Right, so for the first one, this is a very standard biconditional proof. We assume this, then prove that, and then we go the other way around. We assume this, and we prove that for both of them. So let's assume that A subset of C and B is a subset of C, and we want to show that this is true eventually. So, right. Now, suppose X is in A union B. Then X is in A, or X is in B, as usual, or both. Right? If X is in A, then X is in C, because by assumption, A is a subset of C. Similarly, if X is in B, then X is in C, because B is a subset of C, right? If X is in A and X is in B, then X is in C as well, because both of these conditions apply. Thus, in all cases, X is in C. Therefore, A union B is a subset of C. All right, that's one way. Now I have to show the other way. Now assume instead that A union B is a subset of C, right? Now, and then consider X in A, right? X is in A implies that X is in A union B. This is very straightforward, which implies that X is in C. So A is a subset of C. Now if we consider X and B instead, same line of reasoning, X is in B implies that X is in A union B, which implies that X is in C, because we assumed that A union B is a subset of C. So, B is a subset of C. Therefore, A is a subset of C and B is a subset of C. So we've showed that whenever this is true, and whenever this is true, this is true. So we conclude that A is a subset of C and B is a subset of C if and only if A union B is a subset of C. Cool. And now I can move on to the last part, which is going to be part B. C is a subset of A and C is a subset of B if and only if C is a subset of A intersect B. Okay, I'm gonna write this in blue just in case, I mean. So let's first assume C is a subset of A and C is a subset of B. Now, consider X and C. Since C is a subset of A, X and C implies that X is an A. And similarly, since C is a subset of B, X and C implies that X isn't B. So X is in C implies that X is in A and X is in B. So X in C implies that X is in A intersect B. Thus, C is a subset of A intersect B. That's one way, one direction. Right. Now let's assume instead that C is a subset of A intersect B. Then consider X and C. X and C implies that X is an A intersect B. So X is in A and X is in B. Thus, X in C implies that X is in A, meaning that C must be a subset of A. Similarly, X in C implies that X is in B, meaning that C is a subset of B. So C is a subset of A, and C is a subset of B, as expected. Now we conclude that C is a subset of A and C is a subset of B if and only if C is a subset of A intersect B. Cool, and that is all for this chapter. We finally finished chapter 2 and we can move on to some mildly more interesting exercises. About as interesting as pure set theory can be, but you know, we're mathematicians. We're not into interesting things anyway. Cool. Hope this was helpful. I will see you in the next video. Bye-bye.